Okay, buckle your seatbelts. This one's a little bit challenging. That's why I decided to make it its own screencast all by itself. So we're basically following up on what we did the other day, which is Newton's second law of rotations and how torque acts on a system. Okay, so this is a classic type of problem you get in physics where you have basically a solid disk, or maybe it's a roll of toilet paper, whatever, and it's connected to the ceiling. And so it's at rest. We're going to release it and it's going to fall towards the floor. And I want to know, what is the rate at which it accelerates? Now let's think about this. If there was no torque acting on the system, or let's just say there was no force acting on it, it would accelerate it in, right? But there is a torque acting on it, and there's also a force acting on it. So that's what we have to think about here is there's two things that are going to be true. The sum of the forces has to equal ma, and the sum of the torques has to equal I alpha. And the other thing we got to keep in mind is going to make our lives really easy here, and this is a trick we're going to use a lot in this unit, is remember that any of the three basic uh, rotational kinematic variables, theta, omega, alpha, if you multiply them by r, you get their translational equivalent. Theta times r equals delta x, omega times r equals v, and in this case, alpha times r equals a, so therefore a over r is equal to alpha. So we're often going to substitute a over r in place of alpha. You'll see in a minute why it makes our lives a little bit easy here, okay? I don't know if easy is the word, but it helps. I know you look at this like, whoa, Mr. Sam, what's going on here? Okay, how do we go about solving this? So the first thing I'm going to say is, well, I know that the sum of the forces equals ma. I know I have two forces acting on the system. I have mg pulling down on this, and I have tension pulling up on this. All right. And so since there is a tension force, it has to accelerate at less than g. I know that. So I'm going to do some of the forces. I'm going to say down is the positive direction. Remember, always set the direction of motion positive. It supersedes all the other rules, including the right-hand rule. So I'm going to say, well, mg is the positive force and tension is the negative force. So mg minus t equals ma. Problem is, I don't know what T is. So now we're going to come over here and see if we can figure out T, because T, the tension force, that is the one that's making a torque, because gravitation is acting through the center of mass. And so if it's acting through the center of mass, R is zero. So mg is not making any torque, but T is. So the sum of the torques is going to equal I alpha. And so that means the force in this case is only one, and that's the tension force. So tension times the radius is going to equal, now this is a solid disk, and we just got to get used to, I mean, you don't have to memorize this. You'll always be told this on the College Board. I'll always tell you to, but it does help members just go, you know what? Solid disks are a pretty common convention used in this course. And the rotational inertia of a solid disk is 1/2 mr squared. Now that's where this 1/2 comes from. And I'm just going to go ahead and say, well, instead of writing alpha, I'm just going to go ahead and write it, instead of alpha, I'm going to write it as its translational equivalent, because that way I can use it over here. So I'm just going to call it a over r, because remember, alpha times r equals a, so therefore a over r is the same thing as alpha. I said now, basically, I have tension, mass, radius. I'm ready to go. So then now look what happens here. This is really cool. This is going to happen a lot. Because torque is forces times r, I'm going to divide both sides by r. So if I divide this side by r, this becomes an r squared, and this is an r squared in the numerator and an r squared in the denominator. So r just goes away. And I'm left with something quite simple. The tension force is equal to 1/2 ma, not mg, but ma. So now I can take this one here and I can move it over here in place of this one here. So now I'm going to substitute it in here. So instead of saying mg minus tension equals ma, I'm going to say mg minus 1/2 ma equals ma. So I'm just going to get rid of this by adding it to both sides. So now I have mg is equal to 3 over 2 ma. So therefore, if I solve for a, I can cancel my m's out. And I'm just going to get acceleration is equal to 2/3 g. So you're going to practice this a few times. And once you do, I know right now you might be going, oh, what's he doing? But you know what? It really starts to make sense. I'm going to work through several examples of this, and they're all going to go the same way. And so when you practice them in class, you'll see it's really not as challenging as it seems at first glance. Okay. Now the other thing to keep in mind is once I know what A is, I can figure out what T is, because I can just so I can just come here and say, well, if T equals 1/2 ma, then I can just put in this 2/3 here for A, and I can solve for tension. Remember these Atwood machines? Okay, this is a modified Atwood on a horizontal surface, but let's just take a look at this. Okay, so we definitely want to be able to treat Atwood machines, whether modified or like this type of modified or other ones, which we'll get to in a minute. We want to deal with them in a new way. So just think before when we did this, if you recall, I know we're going way back to semester one, but what we did before is we said we always talked about a massless pulley, and if that was the case, please listen here. If that was the case, then the tension force was the same across here. We said, well, of course the tension is the same. It's the same string. It's the same force. Well, that's not going to be true anymore. Think about this. If the tension force was the same on both sides of this pulley, which now has mass and therefore takes torque to make it spin, the here is the same as the R here. So if this tension force, if I had TR here pulling this way and TR here pulling that way, this would not rotate. The sum of the torques would equal zero, and there'd be no angular acceleration at all. But there is. Obviously, this is going to fall down, so this is going to develop a clockwise angular velocity, angular acceleration. So that's what we have to take into account here. But we're going to do the exact same way we did before. Okay, it's really, you're going to see it's not that much. It's no more challenging than what we did before. But just think of it conceptually there. That this torque, this tension force here must be greater than this one here. Otherwise, this would not rotate. Now, on the AB physics test, if they say a massless pulley, throw that out the window, and you could just say, well, you know what? 2mg is the force on the system, and 3m is the mass of the system. So therefore, I can find the acceleration of the system. But now when there's a pulley has a mass, then you've got to use rotational kinematics and rotation and Newton's law of rotation to do it. So again, the sum of the forces is always going to equal ma, and the sum of the torques is always going to equal I alpha. And I know, again, this looks crazy, but let's just walk through it here real quick, okay? So I know the mass of the pulley is 1/2 m, this is 2m, and this is m. Now, clearly, since this is 2m and this is on a frictionless surface, the system is going to move this way. So I'm going to call this the positive direction, and I'm going to throw the right-hand rule out the window. I'm going to say, well, I don't care if this is clockwise. I'm calling that the positive direction. It's going to make my life easier. So let's just talk about what the tension forces are. So this object is going to move this way, and I know the sum of the forces equals ma. So I know that F equals ma for this object. There's only one force acting on this object, is T1. So I know that T1 is equal to ma, right? Because T1 is causing this m to a, all right? Now let's look at this one here. Well, here I do the sum of the forces, and there's two forces. There's mg pulling in the positive direction. Actually, I take it back. There's a force of 2mg pulling in the positive direction. And the tension force is acting against it and losing. So I'm going to make that the negative force, is negative T2. And those two forces, 2mg plus T2, that's the sum of the forces that's going to make this 2m object accelerate at A. So therefore, I can rewrite this for T2 and say, well, T2 is equal to 2mg minus 2ma. So now I've basically described both of the tensional forces in these terms. And I need to do that because it's the tension forces that are making my torque. And so in order to figure out what the acceleration of this now, non-massless, it's a weird term to use, non-massless, but that's what I'm going to say, this non-massless pulley, I have to talk in terms of the torques, which means I need to know what these tensional forces are. Okay, so let's go here. So I'm going to say, well, just as the sum of the forces equals ma, the sum of the torques equals I alpha. Remember, that's just the rotational equivalent of saying the sum of the forces equals ma, sum of the torques equals I alpha. But we got to say, all right, well, what are our torques? Well, basically, I have T1R and T2R. And T2R is winning, so it's going to go in that direction. I'm going to make that the positive one. So I just saved a step here because I was running out of room here. I just pulled the R's out because really it's T2R minus T1R, but I just went ahead and pulled the R's out. I hope you don't mind it did that, okay? Now let's come over here and talk about I, okay? Well, I, for a pulley, it is a solid disk. And so for a solid disk, the I value is 1/2 mr squared. But in this case, my m is 1/2 m, right? So this is m, this is 1/2 m. So I would say it's equal to 1/2 m r squared. That's where this 1/2 comes from. And instead of saying alpha, once again, you get used to this, I'm going to write it as a over r. And just like before, look what happens. I'm going to take this r, I'm going to divide both sides by r, and what happens is Now, well, I haven't done it yet. Okay, I'm sorry. I substituted. We'll get back to that in a second. So now what I did is I took my values here. I said, okay, instead of writing T2, I'm going to take this here. I'm going to take this expression here, and I'm going to put it right here. Okay. And now instead of saying T1, I'm going to put this here. So I get 2mg minus 2ma minus ma times, and all that times r is equal to what we had before, right? Now I'm going to divide by r. So when I divide both sides by r, I have r squared in the numerator, I have r squared in the denominator, so r is gone. I have m across the board, so m's gone. And look what happens. It really turns into quite a... Really, the only trick was this part here. Now what I got is that 2g minus 2a minus a equals, I multiply these together, so I have 1/4 a. All right, now I'm going to say, all right, well, I'm going to have to add a, and then I have to add 2a, so I get an awkwardly numbered 13/4 a is equal to 2g, so I had to divide by 2 to get, actually, I'm going to try to get a by itself, so I'm going to divide this side here by 4/13, and then that gives me a equals 8/13 g. Okay, look, the only time you had to do this would be on an FRQ. You're not going to do this on an MCQ. On an MCQ, what you need to know is if this thing is going to rotate and it has mass, the torques have to be, the tension forces have to be different. If it's massless, then they are the same. Okay, that's what you need to know for an MCQ. But in this case, you need to know how to do all this if you've got an FRQ. But now I know this. Now that I know that A equals 8/13 G, right, which is a lot less than G, which is what we would expect, right? Now what I want to do is let's figure out what the tensional forces are. Maybe we're asked to do that. Well, that's really easy to do because look, if A is 8/13 G, I just take that, put it here. Well, now I know what T1 is. There it is. Well, what about T2? Well, I just take this here, I put it over here, and I solve it. Well, there that is. Okay, and you see, notice, this tension force had to be bigger than this one or it wouldn't rotate. T2 is 10/13 and T1 is 8/13. So, of course, T2 won and it rotated. It's kind of cool. All right, this is a classic Atwood machine. And again, in most cases, your Atwood machine is going to say a massless, frictionless system. Okay, thank you, College Board. But if they don't do that, now we've got to go ahead and deal with the sum of the forces equals ma, and the sum of the torques equals I alpha. And once again, if I look here, just look at this. I know that this is going to have to be the direction of rotation, right? This is going to win because this is twice the force here that is here. But that doesn't mean, now I hope we remember, the tension force here cannot be 2mg because, sorry about that, because otherwise this thing wouldn't go anywhere, right? Obviously, T2 is less than 2mg, and obviously, since this thing is moving up, that means T1 is greater than mg. I'll say it again. When I let go of this, this is moving down. That means 2mg is bigger than T2. This side's going to move up. That means T1 is bigger than mg. Now, let's just go ahead and do what we did before. You're going to see it's the same process again and again. So I'm going to say, all right, so what's T1? Well, T1 is winning. This thing is moving up. So I'm going to say T1 minus mg is equal to ma. And on this side over here, so I can rewrite that and say T1 is equal to this. Then over here, I'm going to say, okay, well, the gravity is winning over here. So I'm going to say 2mg minus the upward T2 is equal to 2ma. And so T2 can be written this way. So now that I have to do this because I need to talk about this rotation, right? So it's the sum of the torques that's going to make this rotate. So T2r minus T1r is what's going to cause this thing to I alpha. All right, so now I'm just going to say here, the sum of the torques equals I alpha. T1 is winning, I'm sorry, T2 is winning over here. So I'm going to say T2r minus T1r, because it's trying to make it go the other way, is equal to, and again, this is a solid disk. I should probably use something other than solid disk, but it's a solid disk, so it's 1/2 mr squared. But in this case, I have 3 m's, so it's going to be 1/2 3mr squared. And once again, instead of writing alpha, I'm going to say a over r. And once again, I'm going to divide by r on both sides. So this becomes r squared in the denominator, r squared in the numerator. That cancels out. Now that leaves me with this. Okay, I'm going to substitute in what I've got here. Okay, so T2 is this. So I'm going to take that and put it here. T1 equals this. So I'm going to take this and put it here, but I've got to remember I have to subtract T1 from T2. So I had to say subtract T1, and that's going to equal to, well, if I multiply this 2, it's 3 halves uh, MA, because remember my R's went away. And now I can make my M's go away. No more M's. And this is pretty easy to solve. And I end up getting up. I couldn't see it underneath my little, oh man, I couldn't see what it is. Okay. But anyway, once I have A, once I say A is equal to, I think this is saying 2/9. I can't really see underneath this little thing on my screen. But once I know that, I can come back here and I can figure out what the different tensional forces are like we did before. Last one, I'm pretty sure. Okay. They like to do this one here, just to make sure you understand that it's that torque is equal to force